So welcome to the second day of the second week, and we have Keith taking forward his lecture. Where he ended yesterday. Keith.
Yeah, thank you, Bala. So good morning. Today's topic, start lower. Today's topic is pulsars. Pulsars are a tiny, tiny fraction of what we think are an enormous number of neutron stars in our galaxy. We think there must be in the ballpark of 10 to the 8th or more neutron stars floating around our galaxy. But the ones we know about are almost all pulsars. As I said yesterday, there are about 3,600 of them. Tiny, tiny fraction. And even if we could see all of the potential pulsars in our galaxy, that might gain us 1 or maybe 2 orders of magnitude, but still it's a tiny fraction. The reason that these completely dominate our knowledge of neutron stars is because of an enormous selection effect. Namely, the pulsations that give pulsars their name makes them much, much easier to detect than other neutron stars. So there could be a neutron star floating by our solar system, not too far away from us, and we wouldn't know it unless it had a significant gravitational effect. But a neutron star could easily escape detection not that far from Earth. So let me give you an outline of today's topics. I'll talk a little bit about the discovery of these stars, unusual stars. I'll talk a bit about the modeling of these pulsars and the electromagnetic bands in which we see them. I'll talk in a bit of detail about timing of pulsars, and that includes both their stability and the modeling of that timing, which is very important to searches, and that overlaps a bit with Alicia's material this week and how you carry out a search for a known pulsar. And if there's time at the end of today, this may spill into tomorrow, but at some point I'll start talking about the evolution and the population of pulsars and what the population breakdown tells us about their properties and how they evolve with time. So let me begin with a discussion of the pulsar discovery. That happened in 1967. Famously, it was discovery by a graduate student working with her supervisor. This was a project led by Anthony Hewish, but the person on the ground doing the bulk of the work, both the construction, or the overseeing of the construction and the analysis work, was a graduate student, Jocelyn Bell. And what they had done was build a large dipole radio antenna. And they did that not because they were looking for pulsars. They had no idea that pulsars existed. They were doing this to study quasars, very distant objects way outside our own galaxy, but ones that emitted detectable radiation in the radio wave spectrum. Okay. And this antenna was based on a relatively simple design, but very clever nonetheless. It was a parallel set of east-west wires that were simply suspended from wooden posts off the ground. It was a relatively cheap way to build a large aperture radio antenna. These wires were 470 meters long, so it was a pretty large scale operation. And the array had a north-south extent of about 45 meters. fact, let me show you a slide. It's a very grainy picture when it's expanded on the screen. So I'm going to go ahead and show a slide. Oh, I guess you have to come down here to do it. Yeah. Maybe I can do it myself. No, I better let you do it. Yeah. Okay, thank you. Okay, so this is a picture, apologies for the graininess of the picture, of these, this array of posts and wires and Jocelyn Bell next to it. This was taken at the time, around the time when she discovered pulsars. If you leave it up for a little bit, the idea of having this array was that it was sensitive to overhead sources in a relatively narrow right ascension. Right ascension being the celestial version of longitude. And by taking those wires that were strung at essentially different latitudes on the Earth's surface, but very closely spaced, by adding delays, electronic delays, to the signals from the different wires, you could, in some sense, direct the antennas, control its directionality toward different declinations. So you had a coherent aperture. So by adding signals from these wires with electronic phase delay, one could, in addition to having picked out a particular right ascension that went overhead at once per sidereal day, one could then also control the declination within a certain range. And that gave a span in declination that ranged from 8 to 44 degrees. Of course, it was a positive declination because this was in the northern hemisphere. I guess that's it for this slide. I can, you can go back to the blackboard display on the screen. Now the data was recorded in those days, this was long before computers were prevalent. It was recorded on chart paper. With a pen. I don't know if you've ever seen one of those gadgets. I'm old enough to have seen such things when I was young. And actually, I've used them. Something analogous to this. The idea was that one expected to see a daily signal if one were tuned to the right ascension, to the right ascension and declination. And of course, as I said, they were looking for quasars. So as a particular quasar would come into view at a certain time of day, they would expect to see a signal. And that was, what they were focused on. But Jocelyn Bell noticed what she famously described as scruff in the data. She gave a very entertaining talk about this subject at my institution last year. She talked quite a bit about this discovery. It was interesting hearing it from her directly. She had some other pictures which I don't have access to that showed her looking over these long trails of chart recorder paper and trying to compare the little scruff on this day with the little scruff on the day before, and trying to line up the sidereal times and looking at different declinations. So she knows the scruff in the data. She didn't know what it was. Didn't look like a quasar. And so she, as a good scientist would, she followed up to understand what in the world this could be. And she was able to verify the reality that this was something real happening out there in the cosmos. There's a long story associated with it. I'm not going to try to repeat that here. I would suggest if you haven't read about it before that you read about it. Really fascinating story of a graduate student, confronting the complete unknown and figuring out what in the world was going on. It was an interesting time. I'll leave it at that, but I do encourage you to read more of the firsthand accounts of that discovery. So the signal that she saw showed pulsations. And these pulsations were coming pretty rapidly. The period was remarkably short. In this particular instance, for the very first detection, it was about 1.33 seconds. And so during the brief time when this star was in the right ascension for that time of day, she would see a set of squiggles separated by this characteristic period. And she confirmed that this signal was indeed consistent with a particular alpha right ascension and declination. Eventually, this star became known as PSR B 1919 plus 21. I'll just point out that the 1919 is a shorthand for the alpha value, the right ascension in hours, so 19 hours, 19 minutes. And the 21 is a shorthand for the declination, so that's 21 degrees. Of course, the accuracy with which its position is known is much higher than that now, but that's a shorthand, so-called telephone number for that source. Now, the period alone, the fact that the period was so short and yet so regular, so reproducible, implied a source that was small. It had to be a source with a structure that was consistent with such a short period. And that meant the source couldn't be all that large. It had to be a source whose structure size was much less than about 1 light second, which is about 300,000 kilometers. And so that suggests it's not a typical star, certainly. It was marginally compatible with a white dwarf kind of interpretation. If you really struggled, you could make a white dwarf model work, but it wasn't natural. People knew about the possibility of neutron stars at that time, but they weren't taking all that seriously. There wasn't strong evidence at that time that they existed, although there was very suggestive evidence. But once the Crab pulsar was detected, it pretty much had to be a neutron star. Crab pulsar was discovered the next year, 1968, and its period was 33 milliseconds. And something with that high of a frequency really demanded an interpretation of a neutron star source. It's not just the dimension, it's also just the speed with which a star would have to orbit in order to give you that kind of periodicity. It's got to be a small star. trying to avoid that conclusion. So the canonical model that we use to understand what's going on in these stars is the following. We imagine a star that is, oops, I don't want to step on that. Another piece. So we imagine a star that is spinning at some angular frequency omega, and it has a radiation beam I'll talk about in a moment. Let's not worry for the moment about what this thing is, but there's some mechanism that sends off radiation in a certain direction. And as the star spins in this direction, say, then that radiation beam is going to sweep around the sky. Now, if it should happen to be that the Earth is over here, then we'll get that radiation. We'll only see it once per cycle as the star sweeps around. This is the lighthouse model, for obvious reasons. And I should say that nothing on this diagram is drawn to scale, absolutely nothing. Okay, just to give you a schematic idea. Okay, the distance between the Earth and the star, the size of the star compared to anything else, none of that's drawn to scale. But it does give you some notion. So this beam sweeps over the Earth once per cycle. That's if it sweeps over the Earth at all. And of course, there are a lot of pulsars out there that are pulsating away, but their beam doesn't point toward us anywhere in that cycle, so we don't know they exist for the most part. The pulse shape is not always simple, and it's not even always symmetric. Let me show you a sampling from the Lorimer-Kramer text of what these pulse shapes look like. I'm showing another slide. I guess I can just I got come up, but it's not responding to, oh, maybe I clicked the wrong thing. I guess I need to go into full screen mode for, there we go, thank you. Thanks. Okay, so, oh, that's not the, oops. Go back one more. There we go. Okay, thank you. All right, so this is a sampling from the Lorimer-Kramer text of pulse shapes from an arbitrary set of pulsars. And as you can see, they have enormous variety in their structure. So this is an average over many different pulses. I'll talk a little bit more about that later on. But each pulsar typically has its own signature, where if you measure enough pulses, build up statistics, it looks like this for that particular star. And in fact, pulsar astronomers learn to recognize a star from the pulse shape, setting aside having, knowing its right ascension and declination and frequency. And so you can see that we have some complicated structures, single pulses but have structure within them, substructure. And in some cases, we have what appear to be double pulses. And those double pulses can arise when you have a radiation beam like this that is tilted down close to its own equator with the Earth visible, or to the Earth it's visible. So you get the beam, and you may get a corresponding beam over here. I didn't show the partner, but it's not unusual at the other magnetic pole for there to be another beam. we typically only see one, but if the orientation is right, we can see two of them. And these are associated, as we'll see later on, with, we think, the magnetic poles of the star. And so we get double pulses if the beam, which we think, at least in the case of radio pulsations, is associated with magnetic poles. Oops, let me just make one pole there. If that is tilted to an angle, a polar angle, near theta equal to pi over 2. And you can go, oh, maybe I can do it myself. I can go around and do this. I guess I can stop sharing. There we go. Great, that was easy. Okay, so this pulse shape, as I said, is recognizable to a radio astronomer who studies a particular star. And as I said, it is an average over many pulses, but you can take a lot of pulses in a relatively short period of time, especially if it's a high frequency star, low period star. But this pulse shape average is generally pretty stable with time. That is to say, if you look at that pulse shape in November and then come back to it the following June, it looks pretty much the same. And if you come back to it 10 years later, it often looks pretty much the same. Structure hasn't changed very much. And that suggests that precession of these pulsars is not common at all. You might naively have expected that precession would play a role in some of these stars, especially the ones in binary systems, yet it's relatively rare. Okay, I'll come back to that point a bit later when we talk about gravitational wave emission. Now, this emission mechanism, which I've drawn very crudely in this cartoon, is just a ray or a spotlight beam coming off of the magnetic poles of a star. This is one of those mechanisms that is famously not well understood. And what that means is that we really don't understand it very well at all, but we think that we have a crude outline anyway of how it works. And that's what I'll present to you. But be aware that this is not something that is understood in detail. But let's go ahead and proceed with the standard model, so to speak, of this pulsation emission. So broadly speaking, we imagine a rotating magnetic field due to these magnetic poles that are tilted with respect to the spin axis, just like we have here on the Earth, but in some cases, obviously much more extreme than that. This rotating B field gives rise to an electric field that is basically minus the cross product of the velocity at the surface, or anywhere in the star for that matter, cross product of the velocity with the magnetic field. And more explicitly, that velocity itself is a cross product of the angular velocity vector and the position vector with respect to the center of the star crossed with B. So we expect that in a star that has a magnetosphere or inside the star itself, these kind of conditions hold because we are basically dealing with a conducting medium, and it's in some sense, it's an extreme case of the electromotive force. And this electric field, which we'll look at the values of later, is strong enough that it extracts electrons, not so much ions, but definitely electrons, away from the neutron star surface. So it creates a plasma surrounding that neutron star. It's a plasma with a fairly high density of electrons, as we'll see later, positrons, in addition to ions. All the erasers are down here. And so that process makes for a plasma magnetosphere. And I'm going to present a very simplified and really oversimplified model of such a pulsar magnetosphere. It's one that you'll work with in your exercises later today. I just want to give you some sense of the electrodynamics of this rotating magnetic field. So let's look at a deliberately oversimplified model that is amenable to analytic analysis. So this oversimplified model deliberately chooses the magnetic field parallel to the angular velocity vector. So we're going to assume that we have a steady state in which we have co-rotation of the charged particles in this plasma with the rest of the star. So all of the ions, electrons, have a common angular velocity. And that's true, in some sense, both inside and outside the star, although you'd have to be careful if you tried to apply this model very deep inside the star. But probably is not such a bad description, not too far below the surface. And so this co-rotation requires that we be in some sort of a steady state equilibrium. After we have set up the charge separation, essentially by ripping charges out of the star. So we've created the plasma magnetosphere from charges within the star itself. This plasma is co-rotating with the star. And it must be the case, once we've set up that charge separation, that the electric field plus omega cross r, instantaneous velocity at an arbitrary location, crosses the magnetic field, that sum must be 0. Otherwise, we would just rip more charges out and create the charges that we need, essentially to kill off that net electric field, the net electromotive force from the Lorentz force. Note that it's helpful to remember this, that given this definition that E is basically minus this quantity involving the cross product of the velocity with the magnetic field, it must be the case that the dot product of E and B is equal to 0. And given that we have this relation involving the angular velocity vector, you can show pretty easily that both the electric field and the magnetic field are in what you might call the vertical plane. That is to say, there is no phi hat component, phi being the azimuthal angle in spherical coordinates. Okay, so let me draw a diagram. And as I draw the diagram, let me impose an additional constraint that we must satisfy from Maxwell's equations. The charge density is obviously constrained by Gauss's law. So let me write Gauss's law in differential form. In your exercise, you'll be applying Gauss's law in both differential and integral forms in different steps. But in differential form, we know that the divergence of the electric field is the charge density rho divided by epsilon naught. And as you'll show in this exercise, this separates the magnetosphere into distinct regions. Characterized by different net charge signs. Let me try to draw a diagram. It's a little tricky to do this on the board, but here's, in some sense, one quadrant of the surface of a neutron star. So this is representing the neutron star here, and I want to understand what's happening in the magnetosphere outside of the neutron star. So let me draw one of the magnetic field lines, assuming that I have a pure dipole. Now remember, I'm assuming here that the omega vector is pointing this way, and for convenience, for analytical convenience, I'm also assuming the magnetic field is pointing in the same direction, even though we know that, or we think that pulsations arise primarily from a tilted magnetic field. But just for getting some understanding of the process, let's align them together. Okay, so let me just draw one of the dipole magnetic field lines. Looks something like the following. Comes out like this, and then down at the equator it should be pointing straight down. So this is one dipole magnetic field line. It's in the vertical plane, where I'm defining this to be the upward direction. And if I infer what the electric field is doing, it looks something like the following. It has to be pointing at a right angle to the magnetic field everywhere. And it's also, as I said, has to be in the vertical plane. And so it looks something like this. And then down here at the equator, it's pointing straight up. Okay. And if you then look, imposing this constraint from Gauss's law, you find that the charge density is generally negative out here in the polar region, and it's positive when you're closer to the equatorial region. And in fact, there's a well-defined line of separation between them, which I haven't drawn all that accurately, you'll see in a moment. This is known as the null line. That corresponds to a net charge density of 0, meaning there's as much positive charge as there is negative charge. And in your exercise, you will find that null line. I should say that this model, the aligned rotator model as it's called, not only predicts that there is this charge separation, and if you look at it closely, you'll recognize that as essentially a quadrupole charge separation, but that also implies that there's a monopole. So this model implies an electric monopole, that's to say net charge, that can be modeled as being at the star's center. And that's in fact a natural place to model it being if you try to extend this model of the magnetosphere into the star itself, which is also a conducting medium spinning in co-rotation. And just as an example, if you compute the total amount of charge, what you get is about 10 to the 13 coulombs, or a star with 12 kilometers radius, magnetic field of 10 to the 12 Gauss, and a spin frequency, cycle frequency of 100 hertz. It's a significant amount of charge. It must be inside of that star in order to set up the charge configuration on the outside that has a quadrupole pattern. So in addition to this monopole, we also have this electric quadrupole. That is to say, an L equals 2 pattern with azimuthal symmetry. So this model is telling us that we have a charge in the polar regions, as I've drawn in the diagram, that is opposite in sign to what we have in the equatorial regions. And you will show that the sign flips at an angle theta that's about 55 degrees. That's what you should find for the location of this null line, which I haven't drawn very accurately. Okay, so that's a nice, convenient analytic model. But as I said, we can't really take it too seriously because we know that the stars of most interest to us, the ones that have very clear pulsations, must have a tilted magnetic field. So I'll just caution that you shouldn't take this too seriously, but it is suggestive of the kinds of physical mechanisms that we need to take into account. So it is qualitatively suggestive of what can be going on in these stars, but we know that the actual magnetic field is very often tilted with respect to the angular velocity vector. And there's something else that is unsatisfactory about this model. If I were to draw more field lines, or to continue going up toward the North Pole and drawing lines that would go further and further out, then at some point I would run into a serious problem. My co-rotation going around the star would involve a velocity greater than the speed of light. So I know this model has to break down somewhere, and we call that somewhere the light cylinder. So co-rotation can't hold indefinitely. It must fail if we get far enough away from the star. It must fail at what is known as the light cylinder, which is defined by the magnitude of omega cross r being the speed of light. So as an example, to get some sense of the scale, if we had a frequency of 100 hertz, that would give us a radius, a cylindrical radius of the light cylinder of about 480 kilometers. And notice that is much greater than the 12 kilometers I just assumed a moment ago. The light cylinder is way out there compared to the size of a star, or 100 hertz. So let me show a slide. There you go. Okay, so this is showing you a model of pulsar magnetosphere. And as you can see, things are not really drawn to scale. The light cylinder in particular really should be much larger compared to the size of the star itself, or if you like, the star itself should be much smaller compared to this light cylinder. But we imagine that an actual pulsar that does have a tilted magnetic field is going to have a complicated magnetosphere where the spin axis, which is straight up, is governing the edge of the light cylinder, but the magnetic field lines are spinning around within that light cylinder, and some of the lines are going outside of the light cylinder. Others are contained within it, and we expect pretty different behavior for electrons, positrons, ions that are in the vicinities of these different field lines. They will tend to stay close to a field line. It's hard for these charged particles to move very far from a magnetic field line, but they can, in principle, move along a magnetic field line. And the ones that move out in this direction are, in some sense, lost. You could think of them as being trailing off behind the rotating star. That doesn't mean they're lost forever. Those charges can come back to the star eventually. Remember that we do have this monopole, net monopole for the star. But it does mean that there's an important distinction between the field lines that close upon themselves and give you a somewhat contained and relatively stable magnetosphere, and those field lines that go outside of the light cylinder. There we go. So these charges that are on the open field lines tend to get lost, at least for a while. And that really defines what we call the polar cap region. It's something you'll address in an exercise today. So the polar cap region is defined by that part of the star where the field lines that come off of the polar cap go beyond the light cylinder. They don't close back on the star. Do you have room over there? I actually have some room here. Let me just give you some sense of the size of this cap, and you'll work it out yourself later on. But the radius of the cap, what I mean by that is the cylindrical radius with respect to the spin axis, is of order 1.5 kilometers times the frequency over 100 hertz to the 1/2 power. So if you have a spin frequency of 100 hertz, you would expect to get a cylindrical radius for the cap of about 1.5 kilometers. Now, the fact that we are presumably losing charge from those open lines means that we need to have a charge source. So in the steady state, quasi-equilibrium, that requires a charged source. To make up for the loss. And it also implies that there are currents in this magnetosphere. There's a lot of theoretical uncertainty about the exact nature of those currents, how they flow, and of course people have tried to model it in some cases in some detail, but it's a pretty tricky business to try and model this accurately. Notice that because of the directions of those those electric fields that I drew back over here, we have potential differences set up along the surface of the star. The electric field has a component that's tangential, parallel to the surface, and so we get potential differences set up between different regions of the star's surface. So there's a potential difference between the pole and the edge of the polar cap that you'll be calculating in one of your exercises. And what you find is that potential difference is of order 2 times 10 to the 13 volts for a particular choice, in this case a period of 1 second. But notice it goes like the negative 3/2 power of that period. So the higher the frequency, the stronger this voltage difference is. And then a P dot divided by 10 to the minus 15, where P dot, well, first P is the period. I've used that notation before. And P dot is dP dt. Notice that the P dot value, dP dt, is a dimensionless quantity by its very nature. So I don't write units for it in the above equation. Okay, you'll be deriving a potential difference in a different form. It'll become clear a little bit later why this particular form involves P dot, because of the radiation associated with this rotation. Okay, well, 10 to the 13 volts is pretty big. And we have this voltage applied over a distance of an order, a kilometer. That suggests that there is a pretty intense electric field. So the electric field above the polar cap is intense. And that means that we get, or at least can get, acceleration of electrons in a region that is also characterized by a high magnetic field. And if you start accelerating charged particles to very high energies very quickly, and you put them through a region of magnetic field, it's not unreasonable to expect that you're going to get some radiation from that. In fact, you get gamma radiation. And those gammas can be high enough in energy that they themselves produce a cascade of electron-positron pairs. And so the positive charges that are in the magnetosphere need not be ions. They don't all have to be ions anyway. If you can produce these electron-positron pairs, you've got plenty of charges to work with. And you have a very strong electric field to help produce them. And you can think of this process as leading to an amplification of the available free charges. And in some sense, it's automatic in that if you have a region, say above the polar caps, where you're running out of magnetosphere plasma to deal with this otherwise extremely strong electric field, well, the electric field is going to produce some more plasma to help fill that gap. Now, that acceleration process is important to understanding the radiation beams that we hypothesize are being shot out of these stars. The location of the acceleration that takes place is not definitive. It's not as if we've been able to send a satellite probe out to a neutron star to take pictures of what's going on. But theoretically, what we infer is the following. So this is not definitive, but it's on at least reasonably solid ground. We think that there are actually two so-called gaps regions where this kind of a cascade process happens. There is the so-called inner gap, which is also known as the polar gap. And that's what I've just described, where you're right above the polar cap. There's a very strong electric field, and that field is strong enough to essentially interact with the strong magnetic field and create electron-positron pairs from gamma radiation. But then there's another gap known as the outer gap, which is near the light cylinder and closer to the equatorial regions. Where you can also have a shortage, in some sense, of available free charges, and that leads to an electric field that becomes intense enough to create electron-positron pairs. As far as radio pulsations are concerned, it's probably dominated by what's happening in the polar gap, but there is some thought that gamma ray pulsars have significant contribution from this outer gap. Now, these accelerated electrons or positrons are going to pass through a region of magnetic field, and in so doing, they can emit synchrotron radiation. Synchrotron radiation. That is in the radio. At higher energies and higher magnetic fields, you may also get bremsstrahlung. And you may produce, in addition, X-rays and gammas. Okay, so the magnetosphere of a pulsar is pretty complicated. There's a lot of radiation happening, charged particles flying off, and lots of electromagnetic radiation associated with that. Let me show you another diagram. we go. This is also from that Lorimer Kramer textbook. And it's showing you a couple of things. First of all, we have what I was discussing earlier, this charge separation between the polar regions, which again, for an aligned rotator, give you negative charge near the poles and positive charge in the equatorial ranges. You see the polar gap, excuse me, the polar cap that is defined by the open field lines that go outside of the light cylinder. So there's the edge of it. And then we have the closed field lines in this region. Now, if you zoom in on this polar cap region, you have what's known as the polar gap region, where you have this possibility of electric fields that are strong enough that you get gamma radiation from interaction of electric field and magnetic field that gives you electron-positron pair production and the charge amplification. So it's just a more diagrammatic way of showing what I was describing on the board. Okay, so again, to repeat something I said earlier, these models are probably oversimplified. Almost surely they're oversimplified. You might even call them simplistic compared to what's actually happening in a real arbitrary pulsar. But these models are probably in the right ballpark. They probably reasonably accurately capture the key processes that govern the radiation that we see from these stars. Bottom line, though, is, and I think you'll appreciate this more after you look at this extremely simplified model of an aligned rotator. The bottom line is that the electromagnetic radiation from these pulsars is extremely complicated. The magnetic dipole radiation that we're going to talk about shortly, in which you simply model this thing as a magnetic dipole is rotating around and emitting radiation. That magnetic dipole radiation is almost certainly important, but not necessarily dominant. Much else is happening in one of these stars. We'll talk more about radiation in a few minutes, magnetic dipole radiation. So I've talked mostly about the discovery of pulsars in the radio band, radio wave frequencies. I alluded to the fact that they've also been seen in gamma rays. They've actually been seen in a lot of different bands over the years. So the pulsars were discovered in radio and in fact, most of the approximately 3,600 known pulsars are seen in radio. Not all, but most of them by far. Let me note something that if you get into this business, start trying to do pulsar astronomy or gravitational wave astronomy associated with pulsars, you will definitely want to know about the Australia telescope. National facility. Shorthand is AT&F. In particular, they maintain a truly wonderful pulsar database, what they call the pulsar catalog. It is in the form of a database that you can query. If you want to try to use it, just Google the string PSR cat, the pulsar catalog, and you'll find it's really easy to use, and it's extremely informative. So if you look in that catalog, you can find that of order 10% of these pulsars are seen either also or only in non-radio bands. In particular, some are seen in gammas, X-rays, the optical even, and even infrared. So they're really brighter sources. So as I said, it's a complicated emission that's happening from these pulsars. Everything is seen. And one thing to keep in mind is that as the stars spin down, as they lose energy from emitting radiation due to the spinning magnetic dipole, as they spin down, losing that energy, we expect eventually that the pulsations will stop. So the pulsations are expected to shut down basically when you stop producing those cascades, when you no longer have enough oomph to do that. So enough room, actually, right here. That shuts down when the following condition is met. When the magnetic field magnitude times the square of the frequency is less than about 2 times 10 to the 11 Gauss hertz squared. So some combination of the magnetic field getting weaker or being weak to begin with, and the frequency spinning down enough, at some point you no longer have enough essentially energy in the electric field to generate the free charges that you need to create those pulsations. Okay, so we know a lot about pulsars because pulsar astronomers have been measuring them for many decades now, and they have very precise tools for measuring the properties of these stars, and that's because they have very precise timing. Much of what we know about pulsars comes from inferring what we can from the patterns of the pulsations themselves. So let me talk about pulsar timing. So first of all, there is some variation in the stability of different pulsars. So some young pulsars are characterized by greater instability. They in fact can be glitchy. We'll talk in some detail later in the week about glitches in pulsars. But generally speaking, if you have a young star, it was relatively recently formed, is cooling down, is spinning down, and its shape is changing a bit. For example, it becomes less oblate as it spins down, but if it has a solid crust around it, becoming less oblate becomes a problem for a rigid crust. So there has to be some give in that process. That's one of the sources of glitchiness. There are others I'll talk about. And some of these stars, these young ones, show very significant randomness, or if you like, stochasticity. In contrast, if you look at older stars, particularly recycled millisecond pulsars, so you learned that terminology last week, right, about recycled pulsars? You have accretion from a companion onto a star, spin the star up. Did you discuss that last week? No, you didn't? Okay. All right. Okay, I'll discuss it. Okay, so these older stars tend to have higher frequencies. And they can have, in contrast to the young stars, they can have extremely stable timing. Now, when I say stable timing, that doesn't mean the period never changes. It just means that you can predict what that change will be. We'll talk about that in a moment in terms of a Taylor expansion, but basically, after correcting for the known spin down, you can predict what the star's behavior will be in the future. So, extremely stable timing after correcting for spin down. And in fact, some of these stars are so stable that they are rivals to, if not better than, some of the best atomic clocks here on the Earth. And in fact, that very good precision, let me start the next column, that very precision has also been used in a very different form of gravitational wave search from what we're discussing this week, namely the use of that precise timing in pulsar timing arrays to understand what's happening in the vicinity of our galaxy in terms of gravitational waves disrupting the metric, that the local metric, local meaning galactic metric. So this has been exploited in the last few decades to search for and perhaps to have found ultra-low frequency gravitational waves that as they travel through our galaxy, they change the timing that we perceive from a particular direction for a given pulsar. So this is basically using an array of pulsars that are known as a pulsar timing array as gravitational wave detectors. So this search has been ongoing for decades, as I said. There's three, actually more than that, now there's several large consortiums around the globe that have looked for this. And as you may have heard or read last year, they are seeing what appears to be evidence now for a non-zero gravitational wave background. And we're hoping that in the next maybe 6 to 8 months, something like that, they will combine forces and give us a coherent single result from all of the different pulsar timing arrays together. And there's a reasonably good chance that when you combine all of them together, you'll have at least a 5-sigma detection. We'll see. And they may have a surprise when they combine them together. But if things go as most of us expect, we'll have a very nice announcement at some point in the future. But I'm not involved in that effort, so I have no inside knowledge as to what they're saying. Okay, now let me talk about what I've alluded to several times now, namely magnetic dipole radiation. The energy associated with that, the energy loss associated with that, what I'll call dE/dt mag, the magnetic component of the loss in energy of the star, is given by, in this dipole moment model, minus mu naught, what I'm calling m perpendicular squared times omega to the fourth over 6 pi c cubed. And so that's just a model you might pull out of, say, the Griffiths text on electrodynamics, where you imagine having a magnetic dipole moment tilted to a certain angle, call that angle theta m, and with respect to the spin direction, and we have some spin magnitude omega. And this quantity m perpendicular is just the magnitude of the magnetic dipole moment times the sine of the angle to which it's tilted. Okay, so one of your exercises, if you're going to this today or tomorrow, but coming up, will be to look at this process of magnetic dipole radiation, relate it to the magnetic field at the surface of the star, in particular the magnetic field at the pole of the star. One thing to watch out for in the literature, and literature, in fact, is not entirely self-consistent. Not everyone's actually used the same conventions. Sometimes the magnetic field that is ascribed to a neutron star is referring to the polar magnetic field. Sometimes it refers to the equatorial magnetic field, and they differ by a factor of 2 in this dipole moment model. So just be aware that there are different conventions, and sometimes there's been actual inconsistency. But we can relate in this dipole moment model the magnetic dipole moment to the magnetic field, what I'll call B pole, and we can then equate this energy loss due to the radiation. We can equate that to the Newtonian rotational energy loss. Now that's an approximation. In some pulsars, we think that's actually a very good approximation. In others, there are other processes going on that also rob the pulsar of its rotational energy. But for the time being, let's make this assumption that this radiation is what leads to the loss in rotational energy of the star as it spins down. And so if you go through that exercise, which you will do, omega dot, which is d omega dt, can be written as minus 2 pi over 3 times the radius of the star to the 6th power over mu naught c cubed, the moment of inertia about its spin axis, I sub z, calling the z-axis the spin axis, times b perpendicular squared times omega cubed. Whereas you might have guessed, b perpendicular is defined to be the pole magnetic field at the magnetic pole times the sine of the angle theta m with respect to the spin pole. Remember, the magnetic pole and spin pole are not the same in general. And this quantity I sub z is the inertial moment about the z-axis. Or the spin axis. Now notice that this equation is telling us that the derivative of this quantity omega with respect to time is proportional to negative some quantity, which I'll treat as a constant for the moment, times omega cubed. And the fact that it has an omega cubed term, that leads to the terminology that this particular process has a breaking index n equal to 3, where we implicitly are saying that d omega dt is equal to some negative constant times omega to the n. And we'll be looking at several different breaking indices this week corresponding to different emission processes. We have n equals 3 for this magnetic dipole radiation. For conventional quadrupole mass radiation, we have n equals 5. And for the R modes I alluded to earlier yesterday, we have n equals 7. Okay, so let's assume that we have that kind of a situation. And let's assume that we have a spin down starting, for example, right after the birth of the star, starting at what we'll call time t equals 0 with some initial spin frequency. And let's call that initial frequency F0. So if we look at some time t later, in fact, I'll call that time tau, referring to the age of the star as we see it now. So we're looking at some star that has existed for some period of time. We don't know precisely when the star was born in most cases. So we'll say that there's some unknown age associated with it. But if it has been spinning down according to this model for that entire time, and that has completely dominated its rotational energy loss, then we can do a little bit of algebra, a little bit of calculus, I guess, to find the relation that tau is equal to F over negative n minus 1 F dot times 1 minus the current frequency F over F naught raised to the n minus 1 power. And so if the star is not too old and F is still comparable to F naught, it hasn't spun down all that far, then you'd want to use this formula. But if in fact you think the frequency is much less than the starting frequency, F naught, and I should just emphasize that this is not necessarily accurate for every star, but we think it's accurate for some, then this simplifies to being tau is approximately F over minus n minus 1 F dot. And in particular, if we have this magnetic dipole radiation, tau mag is of order F over 2 times the absolute value of F dot, because F dot will be negative for a pulsar. Pulsars are always spinning down. And in fact, this equation, I'll go ahead and box it because it's so important when you're reading the literature about pulsars to know that this equation is implicitly used. So if someone tells you the age of a pulsar is a certain value, unless they have other information, for example, knowing something about the supernova remnant that's in, if they're just basing this on the timing, this is what they mean by the age. So this is a common shorthand assumption for what's referred to as the pulsar age. So let's look at an example. Let's look at the crab pulsar, which I alluded to earlier. Crab pulsar is of particular interest because it's extremely energetic and it's losing energy enormously. When I say it's energetic, I mean it's losing a lot of energy. As I mentioned earlier, it's a high frequency star and it's young. Its frequency of rotation is about 30 hertz. its F dot is about 4 times 10 to the minus 10 hertz per second, which sounds like a small derivative, but accumulated over time, it actually adds up. I'll talk about that a little bit later. You would infer from these two numbers that its age is about 1,300 years. The actual age, in this case, we actually know what its age is. Its actual year of age is about 970 years, because this was observed by Chinese astronomers when it happened in the year 1054, 970 years ago. By the way, I just heard this week that Beijing plans to celebrate this millennial celebration in 30 years from now. They're already getting ready to celebrate the discovery of that supernova. If the second frequency derivative is well measured, then one can infer what the actual breaking index is in principle. Then you can find an empirical n from doing a little bit of differentiation. What you find is that the measured value of the breaking index, if it's truly a power law like what's described over there, can be found from the product of f with f double dot, the second derivative, divided by f dot squared. If we do that calculation for the crab, we find that the measured value of its breaking index is around 2.3. So it's not 3. It's close to 3, suggesting that the magnetic dipole radiation model is about right, but clearly something else is going on too. In fact, let me show you a set of measured breaking indices from a small, relatively small sample of pulsars, for ones for which we have well-measured second derivatives. Oops. There we go. Okay, so these are measured breaking indices inferred from this formula, F times F double dot over F dot squared, for a variety of different stars, including the crab, which you can see here at 2.3. Almost all of them have a breaking index less than 3. So based on this, you wouldn't say this is a spectacularly successful model. However, they're not that far from 3 in many cases, and there's even one slightly above 3. The fact that we do have some around 3 suggests that maybe those stars are spinning down primarily due to magnetic dipole emission, but clearly something else is going on in these other stars. Because these I've only chosen well-measured second derivatives here. So from that, we would conclude that the measured value of 3 is not the norm. Something that one might aspire to, but it is not what is routinely observed. So measured value equal to 3 is not the norm. So clearly the dynamics is more complicated. And given our discussion earlier of the behavior of the pulsar magnetosphere, it's not that surprising that it's more complicated than simple magnetic dipole radiation. thing I wanted to comment on is that glitching pulsars have a more complicated behavior, as you might have expected. They show, in principle, much higher, but temporarily high breaking indices. So in fact, let me go back to slides. And show you another set of measured breaking indices. So these are glitchy pulsars. And here, they're almost all to the right of n equals 3. They have ridiculously large breaking indices. But these are stars where clearly something complicated is going on. They're glitching. So we don't think that's magnetic dipole radiation at all. It would, in fact, be surprising if that was the only thing happening for a star that is glitching as much as these stars do. So be aware that if you go to the A18F catalog and you start compiling what you infer to be the breaking indices based on the measured F double dots, F dots, and Fs, you might be in for a surprise if you think they're all going to be around 3. You have to be aware of what else we know about a particular star. So in this 18F catalog, there are about 500 pulsars that have a measured second derivative. That doesn't mean they're well measured. That just means there is a number there that at least one observer reported for some epoch. So be aware that you really want to have a pretty long measurement period to be confident of these values. There are about 18 pulsars. Oops, this is F double dot, not F dot. So F double dot here, and there are about 18 that have a measured third derivative. Okay. So it is possible to measure in some cases. And those are mostly young stars. And it includes the crab. The crab has been extremely well studied over the years, in part because it's so bright, and so many observers have looked at it. Its third derivative of frequency, just to give you some sense of the scale, is minus 2.73, and that's the right number of significant digits for this measurement, times 10 to the minus 30 hertz per second cubed. And there are measurements for which you need to know that. Particularly if you're trying to look for gravitational waves from the GRAB pulsar, you would need to know what that third derivative is, in addition to other parameters I'll talk a little bit about tomorrow. That's a good place to stop for today, since we're at the hour. And we'll talk more about timing tomorrow, and then start looking at the population and evolution. Let me ask if there are any questions. Yeah. Why is there a null line? Yeah, null. Oh, so that's where you find that the charge density is equal to 0. You'll show this. You'll see exactly how it works a little bit later today. So if you apply Gauss's law as a constraint, and you also require that you have a steady state equilibrium where you satisfy this relationship between E and B that you get after you get the charge separation, then you automatically get that behavior. I mean, it's not obvious, but once you work it out, you'll see it has this very nice cutoff in the angle theta. Yeah. I wouldn't say it's always, because I haven't done a comprehensive test, but generally speaking, there's almost always something else going on. And the assumption that you've had a steady spin down of a star, pure magnetic dipole radiation from its birth, is almost wrong, almost certainly wrong in almost every case. There has to be other stuff going on. Just the fact that we're generating all this energy loss from gamma rays means there's something else going on. That's an extra form of dissipation. And we're hoping that, and we'll talk about this later, that there's some gravitational wave emission also playing a role. And we'll talk more about that. In fact, you'll do a simulation later in the week involving a combination of magnetic dipole radiation and gravitational wave radiation. Other questions? Yeah, thank you.